Okay, so I have problem with test question 2. Okay, let me pull up question 2. Okay, so we have question 2 here. Okay, so the question is about hash table load imbalance index and its trade-off with the number of comparisons for a successful search. So let me load the slide for hash table because it's letting me to upload only one slide at a time. So okay, so we went through this class in detail. So some of you were not there, so but let me just quickly explain this. Okay, so you all know a hash table is an array of linked list, right? So in order to set up a hash table, we need to be given the hash function. So if I'm not given you the hash function, you can assume a hash function. And so in this given an array, the hash table is the entries are computed based on this hash function. So if the hash function is say v mod 7, the hash table is an array of linked lists. How many linked lists? 7 linked lists. So the divisor here is the size of the hash table. So the hash table size is 7. It means it is an array of 7 linked lists. So each entry in the hash table is a linked list. Okay, and now we are going to just compute the hash value, which is this reminder. So 45 mod 7 is 3. So that means we are going to add or insert 45 to the linked list at index 3. So initially all these linked lists are going to be empty. So 45 is added to the linked list at index 3. Then 67 mod 7 is 4. So 67 is added to the linked list at index 4 and so on. So after you go through the entire array and you find the hash value, you can insert the elements in the linked list. So if the linked list is already having an element, you append, you add it following that element. So in this case of 45, since even though you already have 45, this is another instance of 45, so you have to just append it. In the case of 88, you already have 67 at index 4, so just append that. So you have seen the code for, you are going to use a single linked list, so we have seen the code for single linked list, how to do all the insertion and so on, and I have given you the code to do all these things. So assuming you know how to work with a single linked list, now we can proceed further. So the thing is, again, to find the number of comparisons, you all know that all you're going to do is just search the linked list. So if you want to search for 30 in the hash table, you find 30 mod 7, it is 3, so that's 2, 30 mod 7 is 2. So index into cell 2 and search for 30 just in that linked list at index 2. So we are going to do 3 comparisons to find the 30. So that's the number of comparisons for a successful search. So if you want to find the average number of comparisons for a successful search, what we have to do is know the number of know the distribution. So you have to build basically first build the hash table, and then how many comparisons you require to search for each element. So for all elements as the first element of this linked list, you need one comparison. For these two elements you need 2 comparisons. For this 30 you need 3 comparisons. So there are 7 elements which require 1 comparison. There are 2 elements that require 2 comparisons. There's 1 element that requires 3 comparisons. So add up this thing, multiplication, divide by the total number of elements, which is 10. So 14 divided by 10, 1.4 is the average number of comparisons for a successful search with a hash table. Okay. Now for the load imbalance index, thing is, so basically trying to find so whether the elements are kind of equally distributed across all the linked list or not. So if you look at this example again, I have the same array of 10 elements, which is probably this 28, this array. Now if I really assume a very large hash table, so in this case a hash table is of size 11, so my hash function is v mod 11. So 22 mod 11 is 0, so that's why 22 is here. 44 mod 11 is 0, so you have 44 here. 78 mod 11 is 1, so 78 is here, and so on. So now in this case, this is our previous hash table of size 7. This is the distribution of the elements. So you see here there are a lot of empty linked lists, which means some linked lists are not being used. So that's the wastage of memory. Okay. So what we are going to find is how evenly the elements are distributed, and this load imbalance index captures that. So it is defined as L max minus L min divided by L max plus L min. That means what is the maximum size of any linked list in this hash table, and what is the minimum size of any linked list in the hash table, and just find the ratio. So the minimum size of any linked list in this hash table is 0, because there are some linked lists with no elements, so that is 0. The maximum size is 4. So 4 minus 0 divided by 4 plus 0, it is 1. So we see that in this terminology you have imbalance. That means the larger this index, the ratio, in this case it can go up to 1 because it's a ratio where the maximum is in the denominator and the difference is in the numerator. So the ratio can go only up to 1, and in this case it is 1. That means that's a maximum imbalance. Whereas if you compute the load imbalance index for this hash table, the minimum length is 1, the maximum length is 3. So it's 3 minus 1 divided by 3 plus 1, so it is 0.5. So that is a relatively smaller imbalance index. So now what is the trade-off? So if you want to find the average number of comparisons for this hash table here, which we found out to be some 1.4, and if you do the math and find the average number of comparisons for this hash table here, it could become less than 1.4. So that is the trade-off. So the more the imbalance, the fewer the number of comparisons. So if you are willing to allocate some unnecessary space, which could be unnecessary because it depends on the array and everything. So if you are willing to allocate basically a larger hash table size, you will reduce the number of comparisons you need. On the other hand, if you allocate a smaller hash table, it is very likely that your linked list in each index could be larger, because you have only few entries in a hash table, so each linked list could get longer. So that means you have to do more comparisons, because in the worst case, if you have all elements getting added to just one linked list, then it's basically like searching for every element in a particular linked list. You're going to spend more comparisons. Okay, so that is the trade-off, and that's what we're going to analyze in that question there. For different array size and hash table size, how these the two values, the load imbalance index and average number of comparisons, come out to be. So I hope this will clear your doubt of what this question means. Now you have to just work with the code. So any questions? Okay. Alright, good. So let me go back and upload the binary, the heap thing. Alright, so we are now back to heap. So just to make sure we get it, we have another example here, so we'll go through this fast. Right, so given an array, the first step is to consider it as an essentially complete binary tree. So it means we have here array of 13 elements from index 0 to 12. So just build a binary tree in top down left to right fashion. So index 0 at the root level, then 1 and 2 at the next level, then 3, 4, 5, 6 as the child nodes of these nodes 1 and 2, then 7, 8, 9, 10, 11, 12. So the last level all nodes are as far to the left as possible, and up to the earlier level it is essentially complete, so everything is fine to make it an essentially complete binary tree. So we are going to consider the array itself as an essentially complete binary tree because you're going to say the internal nodes are from index 0 to n over 2 minus 1. So what is n here? It is 13, the 13 nodes. So 13 over 2 is 6, is integer division. So 13 divided by 2 is 6, and 6 minus 1 is 5. So that is the last internal node at index 5. So from 0 to 5 we are going to have internal nodes. From 6 to n minus 1, n over 2 to n minus 1, we are going to have leaf nodes. So now all we have to do is do the reheapify operation, starting from the last internal node, go all the way to the internal node 0. So internal node 5, index 5, so we are going to compare its data with the data of its two child nodes. We have 70 and 91, 98. So both the child nodes have larger data. So you have to find which child node has the larger data and then swap it. So 98 is larger, so swap 98 with 70. So 70 comes down here, 98 goes here. So you can show the corresponding change in the array also. At index 5 you have 70, at index 11 and 12 you have 91 or 98. So you kind of swap 70 with 98. So 70 comes here, 98 goes here. Now this position that we swap to is like our max index. If you remember, the 12 is the max index, 5 was the index, and we swap. So but this is the leaf node position, so there's no need to check further down. Okay, right, so done with index 5. So we can do at index 4 a similar thing. Like we see here 39, 42, 74. Again both child nodes have larger data, so swap is 74. So 74 comes here, 39 comes down. So again this is a leaf node position, we don't have to go further down. Then in index 3 compared to 14 and 31, 31 is larger, so swap 3 with 31, and then so 31 comes here, 3 comes down here. Now go to index 2. See here 81, 98 and 93. Both child nodes have larger data, so max index is 5 because this child node has a larger data. So swap 81 with 98. So 81 comes here, 98 goes here. Now this max index, this position is not a leaf node position. This is an internal node. So swap, so you have to reheapify further down. So 81 is here. Compare with the two child node data. 81 is larger than 70 but not larger than 91. So you have to swap 81 with 91. So 81 comes here, 91 goes here. Now 81, this position, this is our new max index for that reheapify, the recursive call, and this is a leaf node position, so you don't have to check further down. So we did index reheapify at 2, so we have to now do at index 1. Again 27 with 31 and 74. 74 is larger, so swap was 27. So 27 comes here, we have to check further down. Again 42 and 39 both are larger than 27, so swap 27 with the larger of the two, which is 42. So 27 comes here, 42 goes above. So this position is a leaf node, so you don't have to check further down. So now again this is 55 compared with the child nodes, both are larger, so swap with the larger one. and then 55 comes here, 98 goes here. Again 55 is smaller than both the child node data, so swap with the larger, so 93 goes above 55 comes here, and this is the leaf node position, so yeah, we don't have to check further down. Okay, so with this the we have what, transform the given array or build a max heap of it. Okay, so now what we are going to do is how to sort. So as I said, there are two stages overall. So given an array that we want to sort using this heap sort algorithm, we have to first build a max heap, or we could do a min heap also. So if you want to, for practice, try doing converting this or building a min heap of this array. Okay, so everything is the same, it's just how we check. So for max heap, we check for any internal node the data should be greater than or equal to both child nodes. For min heap, the data should be less than or equal to the two child nodes. So that's the only thing. The code will accordingly change, and with that we can build a min heap. Okay, so now let us stop the recording here.